Hello everybody, welcome to my talk. Thank you for being here, thank you for your interest. We are going to discuss during the next hour about effective transactions management with Spring. We'll look at the concepts and we have some nice demonstration that will show how these things are implemented in practice. I'm Catalin Tudose. It's nice to be here again in Krakow after exactly 4 years. Probably it's my 15th time here. I was doing a lot of trainings, but during the pandemic we stopped and I have now the opportunity to come back exactly after 4 years. My previous visit was October 2019. I am currently acting as a Java and Web Technologies expert and Java chapter lead at Luxoft Romania in Bucharest. Besides this, I am the author of these 2 books that were published by Manning. The first one is JUnit in Action, published November 2020. And the second one is Java Persistence with Spring Data and Hibernate, published January 2023. Our talk is related to some topics from here. Consequently, I brought one piece here that I would like to offer at the end of the talk to someone who would say, provide some interesting note or interesting question. Otherwise, I'm also author of 10 courses and 1 project at Pluralsight, also on topics related on Java testing, Spring, Java persistence. To dive into our analysis of Spring transactions from today, let's remind you a few things about transactions, what they are and which are their characteristics. Probably you are aware of this ACID properties that say a transaction is a group of operations having these ACID properties. When we talk about ACID, we talk about atomicity, consistency, isolation, and durability. First of all, our transaction needs to be atomic. It has a series of actions, and either all of them occur successfully or nothing occurs. We say that the transaction is rolled back. Consistency. We completed the transaction with success or without success. The data remains in a consistent state. Isolation. We are going to experiment a lot here about isolation. We should have some isolation between concurrent transaction because we would like to prevent data corruption. And we are going to look at a few levels of isolation. And durability means that once a transaction is completed, the results are durable, they just don't vanish. So this is the acronym ACID that is shaping the idea of transactions. And we would like to have a look at a few problems that may occur in transactions. The first is the problem of the lost update. We are talking about concurrent transactions in all the examples that we are going to have. We'll talk about concurrent transactions. And we have this transaction 1 and transaction 2 that are concurrent. What may happen so that we have this lost update? Let's say that transaction 1 is reading, you don't see here my pointer now. Okay, is reading a price with value 10. Meantime, the second transaction, which is concurrent, is reading and increasing it. This one says, I read 10 and I will increase, but with 1. This one commits, updates the price in the database. This one updates the price in the database. You see that this one wanted to increase with 1, this one wanted to increase with 2. The final result is an increase only with 2 because 1 update is lost. This should never happen, and we'll see that we will always want to prevent such a problem. This is the lost update problem. But there are also other problems that may happen with concurrent transactions. We talk about dirty read. What does this example say? I have transaction 1 and transaction 2, concurrent. Yes. This one is updating the highest bid. It has to check if the auctioneer that provided this bid has enough funds. Meantime, this one checks which is the highest bid. Oh, 110, while this one will roll back because the person that wants to buy does not have enough funds. So this is a dirty read because this second transaction read something that was not committed and was later reverted to the previous value. Unrepeatable read. Unrepeatable read, to have an example, we have here 2 transactions, concurrent. This one will say which is the highest bid, 100. Meantime, this one will update the highest bid to 110, will commit, and when the first transaction goes on, say, okay, let's try to provide this auction of 105. Meantime, the highest bid is no longer 100. So what was read here is no longer valid. It's an unrepeatable read example, so this transaction will roll back. And phantom reading is also concerned, of course, with concurrent transaction. But now what is changing is at the level of the whole table, not at the level of a particular row. This one will say how many bids are for the item. Okay, I read 2. Transaction 2 will insert a new bid for the same item and will commit. Now I have another value here of 3 that is no longer true for this, what I have previously read. So something happened at the level of the table, a new row was added. I'm not impacting the previously existing rows, but I am impacting the whole table. So these are problems that may happen at the level of the transactions, the concurrent transactions. And we are asking ourselves, okay, if we are aware of what may happen, can we prevent these problems? Is it okay to prevent some of them? Is it okay to prevent only some of them, or is it okay to prevent all of them, and in which conditions? When should I prevent all the problems, and when should I prevent only some of them, and which of the problems may we allow to happen? If we have a look at this table here, you see that here on horizontal we have isolation levels, and on the vertical we have the problems that we have just discussed. Whenever I have here a plus, it means that that problem is addressed by that isolation level. And we see here that the lost update problem is always with plus. It means it should never happen, as I was saying, never ever allow a lost update to happen. So no matter which isolation level we have, even the lowest isolation level, I should never allow a lost update to happen. And as I am increasing the isolation level, you see that we have pluses for the other problems: dirty read, unrepeatable read, phantom reading. Just a moment. So I'm having two concurrent transactions, and I'm asking myself, depending on the isolation level, what will happen in the database. So if I'm having my first transaction, let's say I have one transaction 1, I'm asking myself if the isolation level is read uncommitted, what will the other transaction, let's call it transaction 2, what will it be able to do? So if the isolation level is read uncommitted, and I have transaction 1 that is running, if it is reading a row, the other transaction has no lock, no problem. Transaction 1 is just reading. You see here a minus. It means transaction 2 has no lock. It can read and it can write. But if transaction 1 is writing, yes, here, what can the other transaction 2 do? It can only read, and you see here lock for write. So if we summarize this idea, the other transaction cannot write to updated row, but it can read. Okay, next isolation level that we are looking at is read committed. And you should know that in most databases this is the default isolation level. We'll come back a little later about this idea, but to explain what is happening. Transaction 1 is reading, is here. What's the lock for the other transaction? No lock. So no lock for reading, no lock for writing. Transaction 1 is writing. What can the other transaction do at the level of that row? No, it cannot read, it cannot write. Plus means lock for read, lock for write. So the other transaction cannot read the updated row. So it means if you have a look at these names, read uncommitted, read committed, what should you understand? Here, this one can read uncommitted data. So the first transaction is writing but hasn't committed yet. So transaction 2 can read the uncommitted data, and consequently the dirty read may happen here. So this one was writing, the other one is reading. It has no lock here, and maybe the first one will roll back and the second one will be impacted. While here we say read committed, read only what has already been committed. Don't read something that hasn't been yet committed. So if I'm writing with transaction 1 there, transaction 2 will be locked both for reading and for writing. Next isolation level says repeatable read. So if transaction 1 is reading, the other one can read but cannot write. We have lock for writing. Because if we allow this lock for writing, if we allow this writing, here this one is reading, this one is writing, and we may encounter this unrepeatable read problem. But our isolation level is called exactly like this, repeatable read. So if I read several times from transaction number 1, I should always get the same value. I don't care about what other transaction is doing. I have this safety of the repeatable read. And serializable, which is the highest level of isolation. You see, it prevents all problems. So if one transaction is interacting with the table, the whole table is locked. The other transaction cannot do anything else until the lock is released. Okay, you see that as far as we increase the isolation level, we prevent more and more problems up to the serializable that say everything is safe, no problem from the ones that we have described here may happen. So one question may be, which level of isolation should we pick up in our design, and why not pick up the safest one, the one that allows the highest isolation? The problem is, of course, that transactions and lock do not come for free. They come with an overhead. Serializable, as the name says, will serialize the execution of all transactions. So transactions will wait like in a queue and will execute one after the other. This may be terrible in a real system. Imagine that all people from here will browse for an event like a concert or maybe this JDD conference to pick up some tickets. So you may wait and wait and wait until your turn comes. You cannot even access to read what's happening. This is terrible, and a realistic system cannot act this way. We can reduce the level of isolation with the possibility that some problems occur. For example, someone started a transaction to pick up a ticket, yes, and until we arrive to the payment, yes, that ticket has already been sold to someone else. This is unpleasant, but for sure it is much more affordable than in the case of a serializable. So in realistic systems, when we have a high level of transactionality, of course that will be much more realistic to do, even if it does not remove all problems, as I was saying. Okay, it's the time to have a look at the example, because besides what we presented here about concepts, what transactions mean, the isolation levels, the problems that they address, we want to see these things in practice, for sure. Okay, I prepared here for our demonstration this project in Java that is dealing with two entities. We have the entity item and the entity log. I'm saying we are having entities because we annotated them here with entity. This is an annotation coming from the persistence, from Java persistence. And it means that this is not just an ordinary class, but it is associated with a table. The same here for log. Here I provided a custom name for the table. Otherwise, here the name of the table will be log. I'm having an ID with a generated value for both of these fields ID from log and from item. It means that it is ID, so the annotation ID means this is a primary key. Generated value, don't bother to create a value for it by yourself, because it will be the database that will provide an appropriate value. So an item has name, description, highest bid. As in our examples, we are in an auction. We have an item to sell, and people start to say, I'm bidding 100, I'm bidding 110, and at some time we are having a highest bid. Getter and setter, of course, no art constructor. These annotations come from Lombok. This is a library that will allow us to write less code and to provide, through this meta information, through the annotations, will provide usual things like the constructors, getters, setters, things of this kind. They are not related to persistence, but as we used them here, of course, we have a look at them. And log, something similar, no arguments constructor and getter and setter. Okay, I started here an application, and I would like to to interact with it. How am I interacting with repository? You see here that I came with this interface item repository that is extending JPA repository of item and long, and also some item repository custom. This JPA repository comes from Jakarta persistence, and if I'm generifying it by item and long, it means that it is managing items, entities of type item, having IDs of type long. So exactly what we were having, item with ID of type long. JPA repository comes with a lot of declared methods and other methods that are inherited from some other interfaces that it extends. You will not see here implementations of these methods. They are everything that you may want in general to do when interacting with a database. Find all, save all, whatever, delete. These are our regular CRUD operations. How can we benefit from them? Spring, as I am extending here JPA repository of item and long, Spring will say, I know what you want to do, among others. I know that you want to interact with this entity item, and of course you would like to have something like find all. As you are extending here JPA repository of item and long, I will translate this find all in select all from item. So Spring will take care of creating a proxy class that will implement this item repository, and it will provide the implementation of all these methods or these regular methods that we need in order to interact with the database. Plus, I came here with this item repository custom. So I'm coming with my own methods. They have an implementation here in this item repository IMPL. Spring Data is very smart and will say if you extend here JPA repository of item and long, we explain that it knows what to do. If you extend item repository custom, so another interface, I will look for an implementation called item repository IMPL, and I will find there the implementation of the method. So you see here that here I'm really writing some code. I'm not relying on any proxy in this case. The same here for log repository, that is extending JPA repository of log and long, so it is managing entities of type log having primary keys of type long, and the log repository custom having this implementation. We'll come back to some of these methods. Okay, so this is our infrastructure, and I want to test how it goes. We were just talking about isolation, and I have emphasized everything that is here with this transaction isolation levels. Good. Let's have a look at this method here. We have this transactional test. It's a JUnit 5 test with a transactional annotation. Yes. And we say here isolation should be repeatable read. If I skip this isolation, it will take the default value, which, as I was saying, is read commit it. But let's see what is happening here. You see that I prepared here a breakpoint, and I want to demonstrate repeatable read. How we have first transaction having repeatable read and another transaction that would like to run as our first transaction is running. So this one will read the highest bit of the item twice. Okay, I stopped it. So our transaction is running. If I look here in the console, okay, the highest bit is 160. And now, another transaction comes from here. Someone else will say, I want to give 10 plus to have the highest bit to be the current one plus 10. Okay? Should we wait? If we wait now forever. Because this second transaction cannot advance. So we have this repeatable read here, and the other one is locked. So I say from here, I want to be able to read and reread the same information in my transaction and always get the same result, repeatable read. So you, transaction number 2, wait. I will not allow you to do this until I commit from transaction 1. Let's go back here. Repeatable read 160 once, 160 twice. The other one was released now and was able to increase the highest bit to 170, but only when the first transaction released the lock. Okay, but I was saying no one will force me to provide repeatable read. Let's see what is happening if I remove for the moment this isolation repeatable read, and I will rerun it just like the previous time, having here this breakpoint. So transaction 1 is again running. It stopped. We presume that it's a long-running transaction. Now transaction 2 will say, I would like to update. Any prognosis, any forecast about what it is going to happen now? Hope this one completed this time. So it's no longer waiting. If I switch here, resume, 170, 180. So I read twice the same item, but now my reading is no longer repeatable. I lowered the isolation level. Consequently, I allowed the other transaction to do something and to commit, but my reading is no longer repeatable. Okay, second demonstration. Now with serializable. I said that serializable is the highest level of isolation, and it will not allow anything to happen. I inserted here breakpoint. Okay, how many items do I have? I have 5 items. And I come here with another transaction. Let's add something. No, it is waiting. It is waiting because this one is serializable and says no one else should touch this table while I have locked it. Let's go back here, release it. That's okay, still 5. If I look here, this one was released, committed. Okay, but let's play with the isolation levels as you may have expected. Now I lower the isolation level of the transaction. So I will take the default one, read committed. So I will not be so isolated. And I'm doing absolutely the same thing. Okay, here I have the 6 ones. Let's add this one. You see this one completed. It is no longer waiting for the other transaction. So if I go here and I release it, I had 6 and now I have 7. Something happened in the table. One new row was added because I lowered that isolation level and I allow this to happen. And of course, you may play with all these transactions and isolation levels a lot. We just demonstrated here with 2 concurrent transactions. When you design a larger system, you may think about, okay, what should we allow, in which conditions, which will be the consequences, how much may we lower the isolation level, or how much can we get the isolation level higher so that our system works as expected. Because in a high concurrency system, you may understand that there may be some real issues. Either you have a long execution time, or if we allow a lower isolation level, then things may happen. Dirty reads, repeatable reads, unrepeatable reads, phantom reads. So we have a trade-off between the isolation level and the safety of our transactions. Okay, let's go back to the slides here and tell you a little more about other parameters that we have here. Propagation. Besides isolation, one of the other parameters is propagation. What's the conceptual idea here? We have 2 bins. Let me get this laser again. Say I have bin 1 with method A, which is executed within a transaction 1. And from here, I am calling method B from bin 2, which is executed, and I'm asking myself, is it executed transactionally or not transactionally? If it is transactional, do I have the same transaction, or which transaction? The answer is, it depends. It depends on the propagation parameter. And here, you see, I'm having different propagation for the transaction. This is the default, says required. So if I don't specify any propagation, it will take the required. So if I encountered a method here, yes, that is annotated with transactional, If there was no transaction before, it is required, so I have to start it. It's T1. If it was existing before, it was required, but I'm satisfied with the fact that it exists, so I will continue with the same transaction. This is the most common situation, but we may have a requires new, for example. I picked up one also that is from here that is also pretty much in use. Requires new will say there was no transaction before. I have to start a new one. There was a transaction before. I need a new one. So I will suspend T1 here, and I will start another one, T2. And you may see here other options for the propagation. But let's have a look at examples, because this is something that you may get pretty easily. I think you may get the slides, you may get the code on my GitHub page. You are waiting for it, of course. Okay, let me go back here. And I'm having another demonstration here with propagation test. Let's have a look at 1-2 examples from here to fit in time and to allow you to discuss, to raise questions. So let's see here. So I'm adding here 3 items. Yes. If I look in the implementation, it is here. What it is doing? It is a transactional method. We'll say first I log something, then I will check maybe there is a duplicate. Yes? What will happen with this duplicate? Oh, if it is a duplicate, it will throw an exception. Throwing an exception will mean roll back the transaction, unless I instruct it otherwise. But here I don't instruct it in any way. So duplicate item name exception extends runtime exception, so I don't want to recover, of course, from it. If you come with a duplicate here, I don't allow, and I throw exception, and I roll back the transaction. But let's move just a moment. Let me close a few things here. So I was adding item. Yes, I was logging this one first. If I look here in log repository, this one, here, let's note, transactional propagation requires new. So if I arrived here, transactional, I call this method, which is still transactional, but it will be executed on another transaction. So this add item is executed on transaction 1. Log will be executed on transaction 2. If this check name duplicate throws exception, what will happen? A transaction will be rolled back. Which one? This one from add item. This one, this line of code was executed in a separate transaction and is not impacted. So otherwise I may say, no matter if saving my item succeeds or fails, I want that saving my log always succeeds. I don't allow duplicates in items, but I want to keep the history in log. Here it was okay, here it was okay, here it failed because it was a duplicate. So if I go back here to my propagation test, let's get back to what we're saying. So I'm having here 3 executions of this add item, and now I come and say, somebody is saying item 2. highest bit to 100. This one, you see, should fail. I'm expecting it to fail. And you see, this assert throws from JUnit 5 will say, I am having here, really expecting a duplicate item name exception. But when I come back and check, I will say, how many records will you have in item? 3, because it was 1 to 3 and this one failed. How many records will you have in log? 4, because even if you failed here to add an item, the log should be there. Let's execute this one. So you see here that my test is successful, saying indeed you have 4 records in the log and 3 records in the items. And of course, there are other examples here. You can go here to my GitHub. You can get the code and do a lot of experiments by yourselves. I'm looking forward to some questions. We have just the right time for the questions. Meantime, if you are interested about any of my books, you can scan these codes. You can find them on the Manning website with a 40% discount for the next 3 months.